Hello guys, welcome back to my channel. It's been a long time again. I've just been trying to adjust to the new schedule I have back in India. Jet lag hit me pretty bad this time. But in this video, I would like to talk about some applications of Fourier and Laplace transforms, especially in the context of ordinary linear differential equations. So let's get started. The very simple case that I can consider and that will motivate this discussion is going to be the block spring oscillator. So I have a block of mass capital M, and it's on some surface, sliding on some surface. Not really sliding frictionlessly because we have a frictional force. But first, what's more important is when I say spring, I really mean a spring. So you have a spring like that, it's connected to some fixed support. Okay, this is say like the equilibrium point. So this is say x of t is displacement from the equilibrium point. As I said, if this is like the velocity, if it's moving forward, the friction has to point the opposite direction. So I'll have a minus alpha times x dot, and the dot represents the first time derivative of x. And of course, the force from the spring is the restoring force given by Hooke's law. So it's minus kx in the opposite direction to the displacement. But this is also driven, so it's not really operating at its natural frequency. It's going to be driven by some external driving force d of t, which is periodic naturally, function of time. Now, to write the differential equation for governing this system, it's simple. It's just use Newton's second law. So we have to add all the forces, and that equals mass times the second derivative of x, which is acceleration. That's Newton's second law. So say mass times acceleration, which is second derivative like this, equals, we have to add all the forces, so there's going to be a bunch of negative signs here. First of all, the main force that's really doing all the work, or most of the work, is this driving force d of t. Everything else is sort of a dissipative force. So we have a minus kx of t minus alpha dx of t over dt, which we can rearrange nicely to get m second derivative of x with respect to time plus alpha times the first derivative of x with respect to time plus k times just x itself is equal to the driving force d of t. This is the differential equation we want to solve. Let's Fourier transform, and you'll see why, because we have this nice property. So the nth derivative of some function x, which is a function of t, is going to be I omega raised to the n, and the Fourier transform of x, so I omega raised to n capital F of omega. So this is a nice transformation rule we know. So this is, we're gonna convert this differential equation into linear equations where we have to just solve for capital X. Maybe I should call this capital X of omega. We have to solve for capital X of omega and then invert the transform to get back x of t. Let's do that. Words are just words. Minus m omega squared, because I omega squared, I squared is minus 1, plus I alpha omega plus, I believe, just k multiplied with x of omega equal d omega. So we can just rearrange things a little bit to get minus d of omega over capital M divided by omega squared minus I alpha omega over capital M minus k over m, which we can sort of find the roots of. But more importantly than that, I'm going to put this directly inside the inversion integral. X of t is 1 over square root 2 pi integral from minus infinity to infinity of minus d of omega over capital M divided by, we can factorize the denominator as omega minus omega plus, omega minus omega minus. The plus and minus are in the subscripts. That's the inversion integral. Now you can solve the quadratic equation to get the values of omega plus and omega minus. I alpha over 2m plus or minus k over m minus alpha squared over 4m squared. So that's pretty much what we did. We found the roots. And now for inversion we have to consider a complex contour integration method. But before doing that, let's just assume, and maybe I'll use another color here. If d of t is just I naught times the Dirac delta of t. Now one thing to notice is that if you sort of compare everything, all the sides of the equation for units and stuff, you'll see that d of t has to be a force, because mass times second derivative of position is force. So d of t also has to be a force by dimensional analysis. So what if we integrate force over some time interval, which is say from minus infinity to infinity? If we do that, in our case it's d of t. So we integrate I naught delta t dt, we get just I naught because it's the Dirac delta. So f dt is what we call the impulse in classical mechanics. I naught, or this delta, I naught times delta of t is called the ideal impulse, because it happens in this it peaks in this infinitesimally narrow window on the t-axis. Yep. Okay, so if that happens, well, d of omega, we can find that out. The Fourier transform of d of t, we can find that out. It's simple. It's I naught divided by square root 2 pi. If you don't believe me, if you're skeptical, please try it yourself. Use the definition, it's simple. And the property of the Dirac delta, obviously. And now we can go back to our inversion integral. X of t is 1 over 2 pi integral minus I naught over m divided by omega minus omega plus omega minus omega minus e to the I omega t d omega. But the integration we are going to have to do on a closed contour, just for the sake of complex analysis, so that we can exploit complex analysis nicely. Okay. What are you gonna do? Well, our contour is gonna look like this. Maybe I can tweak this a little more. Okay, that's acceptable. So you're going like this and then looping back that way. So if this is r minus r, we're looping back, and then imaginary axis. So noticing the poles of the denominator, we have to take a condition into account so that we don't completely make omega plus and minus imaginary. We could, but the residue calculation would get a lot more tedious, a lot more intense than it needs to be. So one condition we can consider is k over m is greater than, let's just say greater, strictly greater than alpha squared over 4m squared, so that the radical inside is always positive, which translates to k is greater than alpha squared over 4m. So there's some limiting value for the spring constant k. So we have this on the imaginary axis, we're going to have alpha over 2m, and then this point is going to be square root of k over m minus alpha squared over 4m, and then this guy's just going to be minus of that. So our pole is essentially going to be it's going to be at this point and at this point, which is well inside the contour. This is the w plane, sorry, the omega plane. Okay. Now if we invert everything, we have x of t is going to be, well, you're going to close this way for t greater than 0, we know that, and then close on in the bottom for t less than 0. So there's no poles down there, so that's going to be 0 for t less than 0. Well, for the t greater than 0, the top case, we have to evaluate two residues. So you have I naught over km minus alpha squared over 4. Maybe I can do a better job of writing this down. E to the minus alpha t over 2m, and there's also a sine part, a sine of square root k over m minus alpha squared over 4m squared times t. And all of this is for t greater than 0. So there's the natural oscillating term, and there's also a decaying term because of the friction. So the oscillations won't last forever, which is probably a more idealistic expectation. Now notice one thing. There is no response or no x of t value before t equals 0, or applying d of t. So, or what's really happening is, if you have this system and you aren't really pushing or pulling it in any direction, it's just gonna stay as it is, because of course, assuming zero initial conditions, zero velocity, zero position, everything, like everything's in equilibrium nicely, this system is just gonna stay there forever by Newton's second law without the d of t term. That's what happens when t is less than zero, because the d of t term starts acting on the system after t equals zero. So before that, we're gonna have nothing. So the solution is just gonna be zero, which makes sense. We have that. We had no poles down there. This is also called causality, because if the cause is not present, then the consequence, the effect will not take place. Uh, One thing to note is a second order differential equation needs two initial conditions. We have a differential equation in time, function of time. So I'm going to call it initial conditions for x, or more generally, their boundary conditions. So we need two initial conditions for a unique solution. But notice that this solution here that we found is unique. Well, why is it unique? Because there's no arbitrary constants anywhere. We know what I naught is. It was given. It was part of the driving force. Alpha, T, M, K, everything else is sort of known. So there's no arbitrary constant. We also know there's no phase added with the sign either. So this means only one thing, that initial conditions must be included in the Fourier transform operation when we perform that, because the Fourier transform is literally like guaranteeing, in a way, that t less than 0 will have no poles in it. That results in the zero causality and everything after that. So how do we treat this? How do we work with this? How do we give it a perspective? How do we understand this? Well, so there's one point, is that the discontinuity caused by the Dirac delta plays an important role. So there's, as I said, there's two perspectives. Perspective number one is look before impulse acts. So that's at t0 minus, which is basically like an arbitrary time before zero, arbitrarily small time before zero, right before the impulse acts. We get x of 0 is 0, and the velocity at that instant, maybe I'll just put 0 minus here. I don't want to confuse you people. Is 0 because of causality. We discussed this before the impulse acts. The system's just going to remain at rest forever. But then if you do this, you must include the delta drive function in the differential equation, so that it's non-homogeneous. That's one perspective. This is exactly what we did when we sort of did the Fourier transform directly. we just plugged in place of d of t this I naught times delta of t. So that's, so in that, when we did that, we're naturally assuming that we're naturally assuming causality, which is a valid assumption for this physical system. So causality is a baked in assumption, because we chose to include the delta drive, or the driving the d of t term in the differential equation. This was one perspective. There is, however, another perspective of solving this problem, and maybe I'll use a slightly different shade of green here. So perspective number 2 is enforce the initial conditions. Enforce the initial conditions right after impulse is applied. So that's going to be time 0 plus an arbitrarily small amount of time after 0, right after the impulse acts. But when you do that, we have to remove the delta from the differential equation. More than delta, the I should say d of t, or maybe just let's just say delta, because delta is what causes the discontinuity. Nothing else will really affect this in such a big way. So that means that if you sort of use another causality or argument here, or like a continuity argument for the trajectory, it should be 0 even after a small increment in time. But the partial derivative, the first time derivative at 0 plus is not going to be 0. It's going to be I naught over capital M. Why is that? And why x of 0 plus is 0, and why is that why does that match with the x of 0 minus? That's because if you have a particle, or in this case the spring block oscillator, this is at 0 minus, and this is what it is at 0 plus. Well, if you take the limit sufficiently small that like 0 plus and 0 minus sort of are like the same thing, or let's just say minus epsilon here and plus epsilon there, and then you take the limit as epsilon goes to 0, these two positions for the block have to match, because if they don't, that means the block jumped. The block had some kind of jump discontinuity. Maybe it like, because if they're not the same, maybe the block was, maybe I should put them under the right, yeah, just underneath each other. Because if say the block's like here on the x-axis, which means it jumped in this infinitesimally small window of time, which is not really plausible. This is a classical system, not a quantum mechanical system. So you want continuity. This is a block. It can just disappear from one point, reappear in less than a blink of an eye. How do we know that it's I naught over M? Well, that's another story. I hope you agree with this. It's because of the continuity of the trajectory. Well, look at the differential equation. Plus alpha, first derivative, plus k, just x of t, is the untransformed differential equation, I naught delta of t. Now what if we integrate all the sides on this narrow interval minus epsilon epsilon, and it's a infinitesimally narrow interval about 0. That's where the delta drive starts acting. We could have had a delta t minus t naught, in which case we would have to expand about t naught, take arbitrarily small intervals about t naught. So in which case it would be t naught minus epsilon and t naught plus epsilon, but t naught 0 in this case. When we do that, we can use fundamental theorem of calculus. We get a difference of first derivatives for the acceleration term evaluated at 0 plus minus its evaluation at 0 minus. This is the fundamental theorem of calculus. This is going to be alpha x of 0 plus minus x of 0 minus. This guy, well, if you take limit as epsilon goes to 0, this interval just becomes 0 to 0, which is integrates to 0. The delta, by the property of being a delta, is going to be 1, so we're just left with I naught. Well, for the sake of continuity, and we sort of found what x at x 0 plus was and x is 0 minus was. This is 0 again for continuity reasons. The particle can't just jump trajectories like that. Now this difference of first derivatives they won't really cancel out. Well, we know what the first derivative at 0 minus is by causality is 0. So that has to guarantee that the first derivative at t plus 0 plus is going to be I naught divided by m, and that's where we got that condition on top. This is the most logical way of doing it. It turns out the delta always is going to distort first, second, all the higher order derivatives after the function itself. So this is a general property. I'm just using a spring block oscillator in this video so that we can at least argue using logical arguments such as continuity of trajectories and causality. In other differential equations that are more general, it's hard to see that. So these are the two perspectives. Using this perspective, you can also generate the same solution, but in this case you'll be solving a homogeneous differential equation, which is an advantage. The disadvantage is finding this I naught over m. The differential equation you would be solving is essentially this, but with the boundary conditions of this. X of 0 is 0 and first derivative is I naught over m, which that's probably why you see that we have a sign, because x of 0 in both cases is 0, so the sign makes sense. If you solve the differential equation this way, you should basically get what we all sort of concluded the answer was, which is this thing in red, piecewise x of t in red. Okay, now this was all Fourier transforms. Application of Fourier transforms. Now, application of Laplace transforms. Before going on to that, let me just remind you of the property. The Laplace transform of first derivative of x with respect to t is going to be s, capital X of s minus x at 0. The Laplace transform of second derivative is going to be s squared, capital X of s minus s x of 0 minus first derivative with respect to t equals 0. You can derive this using integration by parts. I won't really do it. I think I have made a video in the past on a more nth derivative identity. So now the issue is this, in these initial values, x of 0, first derivative at 0. These initial values complicate things. So you would say, why do we even use the Laplace transform if it's so complicated to find the initial value explicitly just for the second derivative or the first derivative? Why do we even do this? Why do we even use this? Why not just use the Fourier transform, which turns out to be way more easier computationally and algebraically to work with? Well, that's because if the system is unstable, so for an unstable system, even if d of t can be Fourier transformed, the response or x of t may diverge in time, which is not really physically possible here because it should be decaying because of friction in the system. So response may diverge in time. So for an unstable system, you won't really get something that's practical, something that works. So we have to consider this. These are minute, subtle differences that I cannot really talk about more qualitatively in this video because we're not doing research, we're not doing an active example. In the research, you would just change gears naturally. So now what do we do? Well, let's just consider the simple driven oscillator. There's no friction now. I'm not saying that we can't solve this when there's friction involved. It's just that when there's no friction, this is naturally unstable because it's just gonna keep on oscillating forever without friction to sort of reduce it down. So we have mass. You can Laplace transform both sides. We get s squared, capital X of s, minus s of x of 0 minus the first derivative of x at the initial time plus k times I believe capital X of x is capital D of s. Of course, I'm underlining because they can be complex. Now if we assume d of t is again the ideal impulse, I naught times delta of t. Again, causality will argue that for t less than 0, x of t should be 0. First derivative of x with respect to t should be 0. So perspective 1, just like before, for t is 0 minus, we have all of these initial conditions, but we also need to include the delta, the drive. So with all these initial conditions, what's going to happen is x of 0, the first derivative, all of them will just disappear. So we're just left with this simple form, m times s squared, capital X of s, plus k times capital X of s equals I naught. So capital X of s is I naught over m divided by s squared plus k over m. And then we can invert this Laplace transform. 1 over 2 pi I Bromwich contour integral of I naught over m divided by s squared plus k over m e to the st ds. Well, the contour and the region of convergence is naturally a real part of greater than 0. How did we see that? Well, it's kind of non-trivial. It's kind of, I don't know, I can't really give a good explanation is just because we don't really have some exponential growth anywhere. None of these time functions are going to have exponential growth, especially not x of t. We sort of know or can guess using physical intuition that x of t has to have some oscillatory term, so it cannot have an exponentially increasing term. Neither does the Dirac delta of t. It's not exponential. So there's that argument. There's also argument that like the poles of this guy are at plus minus I k over m. That's where the poles of this guy are. Maybe I should take the square root. So since they sit on the imaginary axis, we cannot really bring the line of the Bromwich contour line along which we are sort of integrating this thing to be coinciding with the imaginary axis. So if this is say L, then I will have to close it this way. Oh, this is horrible. It slipped from my hand. Okay, it's more acceptable, I think. So if we have something like this, we're gonna have I square root k over m minus I square root k over m. This is closing for t greater than 0. For less than 0, it's the other way. It has no poles in it. It will be 0, and that satisfies causality if you check back again. Again, why do I say the real part of S has to be greater than 0? That's because we cannot bring curly L onto the imaginary axis. So that means the Fourier transform does not exist. And hence we could not go and use the Fourier transform, because non-existence of the Fourier transform itself sort of hints at an intrinsic instability in the system because of the absence of the friction term. Now, this you use this, you can solve, you get an answer, and that's fine. That's perfectly fine. The answer you're gonna get is 0, t less than 0. Duh, causality and this no poles there in the closure. I naught over square root km, the sine of square root k over m times t for t greater than 0. This is kind of expected. It's got this initial sort of amplitude term and a sine oscillating at the natural frequency k square root k over m. Now perspective number 2 is also important to consider. We've literally used the same two perspectives like we did for the Fourier transform. That's the important point here. In this perspective, we're evaluating at t0 plus. We're going to start really considering the system from after the impulse has activated everything. We're going to treat it as if the impulse does not exist independently. It's sort of just there to start the system or sort of create the boundary conditions, and then we're going to start considering the system after it's created those effective boundary conditions or initial conditions. So again, causality means that this thing is also 0. The first derivative, using the similar like integrate the differential equation on both sides approach, gives us I naught over m again. So we have this capital X of S minus I naught plus k times capital X of S equals 0. If you rearrange everything, you're literally going to end up with the same expression for capital X of S. So there we go. the value I naught over m also makes sense because in mechanics, impulse is the change in momentum. So mass times velocities at different points, 0 plus minus. So we just consider the instantaneous momentum about 0, change in momentum about 0. This is 0. We know that causality. So this has to be I naught over m. There we go. This is probably an easier way of. We know what the impulse is. It's, you integrate the force over that interval. You're going to get I naught, which is also the impulse. So this is a nice classical mechanics interpretation for why we have this. And there we go. These are the two perspectives that I think are extremely important when you're considering these. The point is that perspective 2 creates creates effective initial conditions for a homogeneous problem. In perspective 1, we don't really have a homogeneous problem, but we consider causality argument to say that has to be 0 before the delta starts, and that's where we sort of put our initial conditions right before the delta. In perspective 2, we put it right after the delta, so that the delta doesn't exist anymore, because its delta's spent at 0. It's just a spike. That's the thing with the delta. It's extremely localized, the most localized as you can get. So after that, all we have left to remind us that there was a delta is the initial conditions it has caused. So since it's an impulse, it has caused the system to acquire a new velocity, not a new position, because trajectory has to be continuous. It's caused the system to acquire a new velocity. That's where the I naught over m comes in. And then the system just behaves as it would like any homogeneous system with these new boundary conditions. So both of them are consistent. They're just, when do we start measuring and when do we start considering the boundary conditions? That's the question that both the perspectives are answering in their own independent ways. So I hope you like this video. I might make a few more videos to solve different problems, but this is the idea. This is all you do. You just Laplace transform, Fourier transform both sides, make the variable the subject of the equation like this, invert it, do the contour integration nicely, and you should get an answer like this. Try a few more examples if you want, and I think that's it for this video. Peace out.